This is the second session of the machine learning series of BCN Analytics. And today we are here at Universitat of Barcelona, and we are going to have a worldwide expert in deep learning, Joan Bruno. Today he's going to talk about trends in artificial intelligence and deep learning, and also explain us what he's doing with his research. So we hope you enjoyed the session.
Good evening, everyone. Welcome to our new BCN Analytics event. Today, as you can see, we are in a different venue, a beautiful venue, I would say. And the reason is that this event is being co-organized with Universitat de Barcelona, Faculty of Math and Computer Science. So that's great, because this is really what BCN Analytics is about, right? So really making sure that the different organizations, private sector, public sector collaborate, and this is good. So big thanks to Jordi Vitria, because he was really crucial to get this place. So you may remember that in May, we met to start talking about machine learning, and we say, hey, this is a broad topic, so we really decided to do a series of events on machine learning. So this is the second one, this is the follow-up. For those of you tweeting, the hashtag is the same one we used last time, BCN Machine, and that's an easy one. So what we learned last time we met, just as a recap and to make sure we're on the same page, we said it's really like machine learning is getting momentum, a lot of attention, it's clearly a trending topic, which is good. We also learned that this is not a plug-and-play thing, right? So machine learning is not about just putting the machine to work. You really need smart people, resources, time, and we also discussed the risk of overpromising. And I think the most important thing and the most beautiful part of the session when we had like Alexandros from Telefónica and Jose from BBVA, and I think it was really good to see how big companies are using machine learning from an innovation perspective, from a research perspective. But today we want to take a different approach. This is a slide I used last time we met, and I want to highlight something, which is, I went too fast. We want to cover machine learning from different perspectives, right? So that's why last time we had people from Telefónica, from BBVA. Now we have a great speaker. He will be introduced later, but it's a complete different angle. I'm not going to spoil the content of the presentation. You will see that in a few minutes. But before getting into machine learning, let me share with you some exciting news, or I feel excited on that. Which is, 1 second. We are organizing in January a datathon about pollution levels in Barcelona. And again, this is really a great accomplishment, because when we created BCN Analytics, we said, hey, we want Barcelona to become a hub, a European hub for analytics. And we are really excited when we have these beautiful events where we are met. But we also wanted to contribute for the good of the city, right? Because we all live in Barcelona, we love Barcelona, and we had this vision of, hey, Barcelona might be a smarter city. And you know what? I think it's sad to say, in Barcelona, pollution levels are really getting out of control. This was published 3-4 weeks ago. I'm basically saying, for those of you who do not read Spanish, that 95% of people living in Barcelona, so I guess most of us, we are all breathing pollution particles above the threshold that, according to World Health Organization, should be the maximum, right? So that's just scary if you think about it, right? So what we are breathing is pollution. And in fact, this datathon that we are organizing is going to be part of an upcoming exhibit organized by CCCB called After the End of the World. I think the name is very telling. It's really talking about how we human beings have been twisting the planet, tweaking the planet, and push it too much to the limit, right? So in this exhibit, different artists will share from their perspective, the impact of human beings. So the datathon is going to be part of that big event, which is the exhibit. Something that particularly makes us also happy is that to organize this datathon, we are combining efforts from different organizations. So we will have the support of Barcelona Supercomputing Center. They are going to provide a beautiful data set where people can be used for the challenge. I will explain that in a few seconds. We also have the support, of course, of the CCCB. We also have the support of Big Data Center of Excellence Barcelona. and also from LEITAD, which is a research institute, and of course, BCN Analytics. So I think, again, coming back to the initial vision, it's good to see that different stakeholders in Barcelona, we are all collaborating to do something which is good for the city. So Datathon is going to be 20th and 21st of January. The goal is to enhance an existing predictive model. So basically, BCC are already building a prediction on what will be the pollution levels in Barcelona in the next 24 hours, next 48 hours. So the goal of the Datathon is going to be how to improve that existing model. It will be prizes for the winning teams. So that includes money, but also tickets for the Mobile World Congress. So we want really also people to participate because they feel motivated because it's a great cause, but also have some incentives in terms of participation. And if you want to know more details, because it's still a long time ahead, this Datathon, stay tuned. So you can follow us in Twitter. Our account is BCN Analytics. So we will be posting more details about how to join. So if you are really data scientist and want to participate, you are more than welcome. So follow us in Twitter or just after presentations, happy to talk about that. If you are working in a company or an organization that would like to participate either as a sponsor or as a collaborator or as a supporter, feel free also to participate, right? So the date is fixed, the topic is fixed, but there are many things to be done. So we are really encourage you to participate. So with that said, let's get back to the main purpose of today's session, which is having with us Joan Bruna. Joan is based in US, but we are really lucky to have him here in Barcelona. So it's a great pleasure to have him and big thanks for making the effort. So he's going to talk around 30 minutes, and he's going to share with us his view and his experience on the topic of machine learning. After that, we will have time for Q&A. So some of us will be moderated by us, but I encourage all of you to participate and ask interesting questions because Joan has many cool things to say. And then we have to leave this place at 8:30, right? So just for everyone to be, so we cannot stay longer or compared to Mobile World Center where we usually meet. So at 8:30 we will leave we will have to leave the building. And obviously there are some nice places around if some of you want to stay longer and have some time for networking and beers. Just two more reminders. Big thanks to Schibsted. It's one of our sponsors, and thanks to Schibsted, this session is being recorded. So if later on you want to watch best moments, you can go to our YouTube channel and you will see the session. Or also if you know anyone who missed the session and would like to see the content, they can watch it in our YouTube channel. And again, big thanks to Universitat of Barcelona, because it's really like this event was possible, thank you to them. So with no more delay, let me hand over now to my colleague, Josep Marc Mingot. It's hard to call you Josep Marc Mingot. So Mingot is also one of the co-founders of BCN Analytics, and he's going to handle the rest of the session. He's going to present our speaker, and he's going to manage the Q&A session. So all yours.
Well, thank you, Manuel. A quick introduction about who we have here today, because it's an extremely great honor to have him. Joan Bruna is an assistant professor at Kiran Institute at New York in the Department of Computer Science, Department of Mathematics affiliated, and the Center of Data Science since fall 2016. He is currently on leave from UC Berkeley of the Statistics Department. His research interests touch several areas of machine learning, signal processing, and high dimensionality statistics. In particular, in the past few years, he has been working on deep convolutional networks, studying some of its theoretical properties and applications to several computer vision tasks. Before that, he was working at Facebook AI Research in New York, working on unsupervised learning. Prior to that, he was a postdoctoral researcher at Curran Institute under the supervision of Professor Jan LeCun. So without delay, thank you very much, Joan Bruna, and the stage is yours.
Hi, everyone. Hola, tothom. So first, thanks to the organizers. Thanks, Pau, for inviting me here. It's very nice. Do you hear me well? Yeah. Okay. So that was a pretty tough talk to give because I have to adjust. Typically, I give talks to like presenting research ideas, but now in this talk, I will try to do something a bit different. I will try to motivate or justify why maybe on the one hand, machine learning is actually a very interesting field, not just for practitioners, but also for, why is it so popular in the university, in the academic research? And also try to highlight some of the synergies that I've experienced, that I've seen between actually the university and the industry. And so hopefully trying to motivate you to either spend more time thinking basically, but appreciating both sides of the coin. So first I will just, I was introduced very well, so maybe this is not that necessary, but just to give you like another idea of what I'm doing and where am I doing these things. So currently, yes, as he said, I'm a assistant professor at NYU, so this is basically a tenure track position. And what it means is that most of my time I spend it basically doing research and teaching. And so we also have time, we had time to create this new group. And if you are actually interested, we are, in a sense, we are hiring. So if you're interested in visiting New York and spending 5 years basically being not very well paid, but doing awesome research, please contact me. Okay, so I'm here now. And and before that, I was indeed I was at Berkeley working in the statistics department, and I spent some time also at Facebook Research basically on the new AI research lab. So these are some of the basically topics that I worked on. I'm going to probably spend some time later describing more in detail what my research was about. And even before that, so before coming to the US, actually I spent some time doing my studies in France. And in a sense, this is an important chapter on my bio because it's one of the things that one of the things that maybe we could actually get inspiration from our neighbors because they have a really well-developed sort of higher education program. And so just to give you an idea, I did my PhD in applied math in École Polytechnique. And before that, actually, I spent my time, maybe if it's not apparent now, I was actually an engineer. I was working at the startup, and I was not doing machine learning, but I was basically spending my day trying to work on that sort of images. So this is actually in a context that is very different from today. But in a sense, I've been interested in actually not just proving theorems and writing papers, but also interested in actually making things that work. And so, and actually, this is one of the strengths one of the things that I really like about machine learning because it has room for everyone, right? I mean, you can just create an impact by coding something that is goes faster than the previous algorithm, but you can create an impact by developing some theory. And so I'll try to illustrate some of the like recent case studies that sort of you can think them as different chapters, different episodes that highlight some of the synergies, some of the interactions between doing research at the university and collaborations with some company. So I chose these 3 studies. I mean, they are completely arbitrary. The only thing that they have in common is that I'm part of it, right? But just think of them as sort of little examples. Okay, so the first problem that I find kind of interesting is something that we are going to start this fall. And it's with a company that's called SAP. I guess that you know it. So in this is a relatively, it's a rather crazy project because what we want to try to do is to leverage a huge database of employee data that they have in this company. And for example, the CV, all the performance reviews that the employees have, basically all the, different, courses, education updates that they have, etc. And what we want to do in this project is to obtain a kind of a data-driven career advice, right? So it's like a machine learning model that will look at each of the employees and will kind of predict if you want to go up into the food chain, what is the next master that you should be studying, right? Or, well, that's one of the dreams, of course. And also, on the other side, we also want to make this tool useful for the company to, on the other hand, come up with, okay, maybe in the performance review, you should, rather than just, talking and chatting with the employee and, letting your thoughts free, maybe you can have a more quantitative answer, trying to orient these people towards, something that is useful for both parties. And the other goal, so a bit more closer to maybe topics that you have seen in machine learning, is to basically go for this embedding space. I mean, embeddings is a very hot word these days Basically, it's a mathematical conceptualization of this idea that you can relate concepts, right? And how do you relate concepts in math? You put them into the same space, right? So now you can basically consider things like being close to each other, right? Two concepts are close to each other if the two corresponding points are close in that space, right? So you could imagine doing the same thing for when it comes to jobs, right? I mean, you would be just a particle in that space, and your career would be just a trajectory, a path in that space. And in that space, you have basically goals, right? You have areas that basically, you could imagine like, there are territories that are very, let's say, very fertile, right? Like, I don't know, data science maybe might be a territory that is very green right now. So if you are in that space, you would be interested in knowing what are the steps that you need to take if you want to basically move in some direction in that space, right? And so, I don't know. I mean, this is just an illustration. Of course, this is just a picture, but it's an interesting example because it illustrates some of the first challenge that I find quite important, right? That this I can write it down as a sort of a machine learning task. I can abstract that actually the data points are people, and this is actually a danger, right? Because I mean, data points are people, but people are not just images that you collect in the web and just do whatever you want with them, right? You need to be careful about respecting the privacy of the employees. You need to be careful. You need actually to be more than that. You need to be able to certify, right, that you are not using information that you are not allowed to use. And sometimes there's a tension, right? I mean, a machine learning system, as you know, it gets better as it can use more data. But using more data enters a conflict in tension with actually your privacy, right? So how to design optimum trade-offs? This is actually an interesting question. And for example, another problem that we are facing is that, okay, SAP is a large company. I don't know how many employees they have, but it's not, it's a tiny portion of the job market, right? So if you want to make this work useful and something that can teach us something, we need to basically scale up, right? You need to go and talk to more companies, for example, LinkedIn, that you have to convince them that this is actually an interesting project. And these are challenges that are nothing to do with actually the technological challenges, right? Because this is, to start with, a very complicated, non-trivial problem to solve. And so here, I mean, one of the, I say, take-home messages is that you might be in a company that you can basically identify an arbitrage, right? You say, okay, I have all this data, and I'm not using it. I'm just, I'm still having these humans that look at it and make suboptimum decisions. Maybe I can just make data-driven. I can make things work better. And it's not, I mean, my impression is that this is very rarely the case, right? That you have basically an off-the-shelf algorithm that you can just run on your problem and be done with that. It has happened, but it's, I think that the more we get away from, let's say, signal processing problems, the more we have to deal with this overhead, right? In that case, it's a privacy overhead, and it can come up with different forms. Okay, so the other example I wanted to illustrate, that this will be a bit more appealing maybe to the audience that is more closer to academia, is another collaboration that I'm currently enjoying very much, that in a sense tells us about the breadth of machine learning, right? It's not just a discipline that is basically there to help companies make more money. It's actually a discipline that can create huge impact within science, right? And in particular, physics. Physics is a discipline that is, as you can imagine, an incredible source of data, right? But the thing is that many problems in physics that we want to advance, they are not necessarily producing images that look like squared pixels, right? I mean, there's, as you can imagine, in the real world, a lot of measurements, they don't come with the sort of regularity that we have in natural images. And so this is a collaboration with different people. So there's people from CERN in Switzerland, and there's people from the Lawrence Berkeley Lab in Berkeley. And so here what we want to do is to basically advance or use data-driven methods to advance, for example, the detection of neutrinos. So I don't have a pointer, but so this thing here is an illustration of a huge 1 kilometer by 1 kilometer by 1 kilometer cube in the Antarctica. Okay, so it's sitting there, and it has holes that look like these huge cylinders. And why is this thing sitting there? It's because it's there trying to listen to the cosmic rays, right? And there's, in particular, one of the things that is very useful for basically deriving theories about the universe is the basic trying to characterize the neutrinos, right? Basically the nature of neutrinos. And so what does this relationship with the machine learning? Well, so here now, of course, you have a problem that is naturally, it's very far from a standard machine learning setup. The first difference is that how many neutrinos do you have per year? Maybe they have 50 neutrinos per year, right? So it's not a big data problem. And the other difference is that if you look at the grid, like the organization of the measurements, they are not images, right? I mean, typically in images you have a squared regular grid. Right here you just have something that looks like a hexagonal lattice, but not quite. So there are two challenges, right? How do you make very efficient, data efficient models that can operate on domains that are not just natural images, but that they are not squared grids? So I don't know if people here are familiar with traditional computer vision models. Maybe I was assuming that people were familiar with convolutional neural networks. Who has heard about CompNets? Okay, so maybe half of the audience. Okay, well, so I'll try to fill in the gaps. Okay, and the other problem that we have here that is also very related is a problem that arises in the particle accelerator. Okay, so if you follow sometimes that these appeared in the news, 4 years ago, there was this huge boom, there was discovery of the Higgs boson, right? The Higgs boson is essentially something that manifests itself through that sort of events, right? So basically what you have is you put two particles, you make them crash super fast, they break into smaller particles, and basically the way they break, it leaves a trace that can only be explained by the existence of a certain particle. And so what is the role of machine learning here? Again, now that we know what the Higgs boson exists, of course, physicists, they continue, right? They want to basically validate or invalidate the standard model. Okay, so with this, that relates to a technique or a discipline that is called quantum chromodynamics, that essentially measures the geometry. Okay, so basically you have the particle accelerator, and you have a cylinder that sort of detects events that consist in this sort of creation and explosion of particles. And the sort of measurements that you have look like that, right? You have basically a bunch of particles that interact into this cylinder, and we have basically a physical model that tells us that, depending on the distance between these events, we are going to have it's going to be more likely than they will determine the nature of the event. Okay, and so if you look at this data, okay, and the other one, they look very different from images, right? Because images and basically the most of the sort of success stories of deep learning involve data that is sampled on a very regular grid. Okay, that's what I was meaning before, right? So images are basically consist in a bunch of pixels in a rectangular array. If you think about a sentence like speech, you can also model it as a sequential data, and word and speak and text, you can model it as a sequential list of words. But in more general, in general problems, we don't have that sort of regular structure, right? We don't have that structure, so the question is, how do we learn beyond these models? And so one of the things that we are working on very intensively in our lab is what we call this deep learning models that operate on graphs. Okay, so graph, for those of you who are not familiar, is a mathematical framework that basically you can model relationships between points, between features that are very general. Okay, so you can model things that live in if you want to be a bit more fancy, data that doesn't live in a Euclidean space. Okay, you can model geometries that are non-Euclidean. And so we are spending a lot of time and having a lot of fun with that sort of models. And so what is interesting is that now that you suddenly are able to understand how to do proper deep learning on that sort of domain, suddenly it opens up the domain of possibilities. It's not only useful to work on that initial problem of particle physics, but suddenly you realize that if you know how to deal in the language of graphs, you can apply this language in many domains. For example, I will show you some examples in computer graphics. if you have a problem of planning or navigation, active learning, if you, for example, want to learn on social networks are naturally defined as graphs, and also problems in biology and chemistry. So just to give you some examples of how people are using these models to solve new problems. For example, you can do n-body problem simulation. Okay, so it's something that if you, I don't know if you took a physics class in undergrad, that was supposed to be like the ultimate impossible problem to solve and even to simulate, very expensive. We are using these data-driven models to get incredibly good results in that domain. We can also use these things to learn how to communicate. Okay, so that's another funny, interesting project, right? You can imagine that you have basically, you know, the traffic lights. The traffic lights become adaptive to the cars that are incoming. Basically, if you have a system of self-driving cars, you want the system of self-driving cars to communicate each other, right? So that when they are both arriving at an intersection, they can basically, you know, dictate who goes first, right? So maybe, so this, of course, is an update from, you know, our traditional system that, again, people are using these models to deal with that. Another very relevant problem that now we are starting to use to do well on with these graph models is semi-supervised learning. Okay, so just forget about the fancy name, but what it means is that, like, if you basically, you can imagine that this is a network of citations. Okay, so for example, what this means in the academic world, when you write a paper, your paper is sort of connected with other papers, right? These are the papers that you should be citing. And some people, sometimes they forget to cite someone, right? Or, you know, you tend to do clicks. So basically, trying to understand how to do data-driven on that sort of relational data is actually pretty important in applications. And as I said before, another very active area of application of these models is quantum chemistry. Okay, so quantum chemistry is the problem of basically determining the electronic or, you know, energetic properties of molecules. And so, okay, I don't want to bother you with quantum mechanics, but, you know, the properties of molecules are determined by a very complicated equation, the Schrodinger equation, that is very expensive to solve. And there was a breakthrough some years ago that was called the density functional theory. So there's a couple of smart people who learned how to approximate this thing, and they got the Nobel Prize for it. But still, you know, what you see, at least in practice, is that there's still a lot of room for improvement, right? That you can use a sort of a graph neural network to do, you know, to gain 5 orders of magnitude. I think this is for small molecules, okay? So just take everything with a grain of salt, but just to give you a hint of what are the domains where we are applying these things, okay? And another one that I suspect that is going to become huge in the near future is computer graphics, okay? Computer graphics, it's funny because they have basically an incredible amount of data, but it's for some reason it's not as available to researchers as image data. But there, as you can imagine, there are a lot of tasks that involve graphics that could help or that could benefit from basically a deep learning, right? The data-driven models. For example, you might want to, you know, if you are someone who is working at Disney, you know, drawing these characters, maybe you draw a new character, and you want automatically to give this character the ability to be angry, to be happy, to be sad. You don't want to be drawing it by hand all the time, right? So you would like to maybe transfer some of these properties on a new character. So these models allow us to do that sort of things. Okay, and we can actually do also very complex non-linear dynamics. Okay, so for example, we can simulate with these models what would happen if I take a new object and I throw it in the floor, right? And I can, as you can see, well, you cannot see it here because maybe the quality is not very good, but we get like substantial improvements using these models. Okay, this is something I already mentioned. And I don't want to conclude this case before talking about something that I'm particularly excited about, that I apologize if it's getting too much into the sort of techie territory, but what is interesting in this case is that this new language to do deep learning it's useful not only in applications but also in classical domains that you could assign to maybe statistics or theoretical computer science or algorithmics, right? For example, there's a very famous problem in statistics that is called the community detection, right? That basically asks for, under what conditions, if I observe a graph that has two colors, how can I identify the two communities if I hide you the colors? Okay, so this is something that is actually a known problem in statistics that now we are learning how to solve very efficiently with these models. Another application is something that maybe you heard about that is called the traveling salesman problem, right? Which is the problem of you have a bunch of cities, right? You have a route, you need to deliver things to every city, and you have to design what is the route that goes through every city exactly once, that has the smallest length, okay? So this is a problem that is NP complete. Again, for those of you who don't know what is NP, what it means is that it's super expensive to compute, right? We don't know any algorithm that, actually we know that there's no algorithm that can do it fast. So the goal of the game is to come up with approximations that are as good as possible. So we are using these models to basically do better, or like starting to be competitive with the sort of the best heuristics in the field. Okay, so this is just to highlight that sometimes if you go to talk to people who are in the applied field and they come up with their own particular problems, it's actually, this is our bread and butter, right? I mean, many of the machine learning advances, they came by basically motivated by an application, right? I mean, even the original convolutional neural network was motivated perhaps by the problem of reading checks, right? I mean, they needed this technology, and this was a big push to make it better. So this is just an illustration that, yeah, I mean, we researchers in machine learning, we really need you, people who are on the other side, to actually bring us problems that we don't know how to solve. And so, the other thing that I'm seeing here is that in this context, one of the things that I'm observing is that most of the limiting factor, the thing that really takes us most of the time, is actually the software engineering skills, right? Basically, when you just work on, let's say, on a curated data set like ImageNet, someone like, like a team in Stanford spend I don't know how much time preparing the data set for you, right? So now you can just download, run your model, and you're done. If you are working on a new problem, you will have to spend a lot of resources and a lot of time before you can make it ready to actually, to give like good results. So this is something, I mean, it's just a reflection. I don't really know, how can we fix it? Maybe it's just something that we cannot fix, but it's something that I am observing, and yeah. Okay, so now I will just describe the last use case. That's something that I also find quite interesting, and also it also reflects, maybe one of the differences that you can distinguish between, I would say, the industry understood as basically like a web of small companies, and like basically the large tech companies. Okay, so this is a project that I'm currently working on with Max Nickel. He's a researcher at Facebook Research, and so maybe I don't know if you heard about this word embedding technology. Okay, so probably if you are using Google, you are using word embeddings all the time, right? And so I mean, probably you are consumers of word embeddings. So for those of you who don't know, in one line, what is a word embedding? Is a way to it's a mathematical dictionary that translates the word to a vector, okay, in a very high dimensional space. And it's done in such a way that what we perceive as two words that we perceive as being similar semantically, this embedding manages to make them similar in the mathematical sense, right? I mean, you can measure the similarity maybe with a dot product, okay? And then again, if the dot product is something that you don't know, don't worry, okay? These are just 2 points that are close. So this is actually very good, and as I said, it has essentially transformed how we apply machine learning in text, okay? So it has really been revolutionary. And so the question in a sense is that started this thing is, okay, here we are making a sort of a mathematical assumption, right? We are declaring that we want these vectors to be closed in Euclidean space. Okay, so the question is, do we have reasons to believe that words can be sort of well expressed as distances in Euclidean domain? And so it turns out that there are some examples, there are some instances where we know that the answer is no. Okay, so think about like a data set, for example, like WordNet. So what is WordNet? WordNet is basically a database of concepts, right? So for example, you can think about So here you don't see it very well. You don't see it at all. Okay, so basically think about, I have animal. Okay, so then animal is divided into mammals, I don't know, fish, birds, and I don't know, whatever. And then every mammal is divided into different families, right? So the way you think about concepts is not as points in a Euclidean space, it's more like a tree, right? You think that there's some underlying hierarchical structure. And so what it turns out is that if you want to embed some object that has a hierarchical structure that looks like a tree, there's a natural space where you should think about it mathematically, and it's not an Euclidean space. It's something that is called hyperbolic space. Okay, so I don't know here. Okay, don't worry about this. Don't be scared about this word. But basically, it's a space that doesn't look flat, right? It looks like it's a sort of a pointy, so it has something that's called curvature that is always negative. And it turns out that you can maybe visualize this space with that sort of nice drawings. Basically, think about as you have points that get closer and closer to the boundary, they get farther and farther apart. It's like as you get closer to the boundary, you stretch the space. Okay, and so it turns out that the Max and another colleague from Facebook, they realized, okay, maybe we can use that new geometry to maybe construct more efficient word embeddings. And so this is actually a very interesting example that, to me, it really marries very well things that I like, right? So on the one hand, you come up with basically some property that comes from the world, from the real world, like the fact that there's some hierarchies. And then on the other hand, you relate it with a very natural mathematical object. And so, just one of the things that we are now working on, again, this is more for the technical crowd, is that once you think about that your object, that your outputs are not in Euclidean space, but in a new space, you have to rethink some of the building blocks of machine learning. Okay, so for example, if you are using gradient descent, you have to know how to compute gradients in this new space. It's not complicated, but it's something that you have to work. And then there's also a number of interesting things, is that if you can embed things in a low-dimensional space, so now I can basically take a book or like a document, and I can look at how it looks in the disk, right? So now I can think about documents as images, right? I can see this like a particular image in the disk. So now we have the ability to leverage other tools from machine learning, for example, a convolutional neural network, in that sort of thing. So that's an example that shows that, again, you can actually, by combining different tools from machine learning, from deep learning, you can actually, you can create something that is potentially useful. And so this is just something that also I wanted to use as an illustration that, yeah, this is an industrial collaboration, but maybe it doesn't feel very industrial, right? Because it doesn't really relate to a very practical application, right? We try this and we don't know if it's going to work or not. And this, to me, it's something that I really enjoy personally, because it means that you can sort of get the best of both worlds, right? You can be working with an industrial environment with a lot of resources without having to worry about deliveries and all this stuff, right? The question is, well, how could we replicate these things? I mean, maybe the answer is that it's not possible, right? To just have that sort of collaborations beyond like a big tech companies. But I just wanted to mention it. Okay, and now I will just spend like the last 5 minutes or 10 minutes just giving my personal impressions on where is this technology going, by basically just mentioning some current problems that I think are sort of exciting and that the community is kind of working on them. So these are some of the topics that I realized. I mean, of course, this is a very non-exhaustive list. I mean, it's just some of the problems that I think are kind of interesting, things that are happening right now. Okay, so what is the meta-learning? So meta-learning is this, it basically, it's also known as learning how to learn, but it starts with this observation that, as you might have experienced, if you're a practitioner of these machine learning tools, you are still essential to the loop, right? I mean, the human, an engineer that is always, typically very well paid, is there, tuning the algorithm, maybe choosing which architecture, how many layers, how many filters, He's choosing how to train it, what is the loss function. He's choosing which optimization algorithm to use, how to tune the optimization algorithm. He's choosing whether the images should be, I don't know, squared or should be cropped. And so there's all these choices that are, as you might think, critical, right? I mean, this is the thing that can make the difference between a good model and a model that doesn't work. So a current topic that, of course, is interesting to us as a community is the question whether we can learn also this step, right? So basically, can we bring the learning mechanism one step up? Okay, so can we learn how to imitate the human that is currently making these systems work well? So this is a bit like, then you can think, okay, how can I learn to learn to learn? And how can I blah, 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 blah. Okay, so of course, there's a moment where this, of course, this strategy fails, okay? There's a moment where there's no free lunch. But the point is that if you want to do that, you need to basically construct a training set where every instance of the training set is a learning problem, right? So basically, as you can imagine, the number of resources that you need to train this scales and it scales up to a certain, pretty intensively. Okay, and so this is actually, I find it a very interesting and to some extent intriguing direction, because as I said, I cannot see this thing scaling up to to infinity. Like I cannot see learning to learn to learn to learn to learn, but in a sense it's something that can have a huge potential gain, right? I mean, if you are a company and you don't want to hire a deep learning engineer paid like super expensive, you might be interested in the automated engineer, right? You might be interested in actually having an algorithm that does this tuning for you. Okay, another area that I think is very, very important, and in a sense I'm also personally working on that, is what's called the active learning. Okay, so in traditional supervised learning, the learner, like the algorithm, is like this very passive object, right? You basically you just feed the algorithm labels, and the algorithm is just answering yes, no, right? So it doesn't basically, other than changing its weights, it doesn't make any interaction with the teacher. So active learning is actually it's a form of semi-supervised learning where you are asking the algorithm to also decide which information to query, right? You can imagine this is how a children would learn, right? The children is not just learning by listening to what the teacher says. At some point, the children also asks questions, right? And maybe you play this game, right? The 20-question game is something that illustrates why actively asking the right questions can be a big changer, right? I mean, learning how to ask questions is something that is definitely part of an intelligent agent, right? So a path to AI has to solve the active learning problem. Okay, and so it's not a new problem. It's actually it's a problem that is, in a sense, old news to a lot of statistic community. But I think that it's now starting to really catch the attention of like a lot of the deep learning community, and we might very soon start to see end-to-end systems, right? A system that not only learns how to ask the questions, but also use these answers to solve like a solution end-to-end. Okay, and of course, and I just wanted to mention that this is a problem that, of course, is very important in practice. Okay, we have a lot of companies, for example, you might imagine Apple or Samsung. They have these intelligent cell phones, right? That they ship with this sort of technology to do speech recognition. But this thing has been trained over a database of million, like I don't know how many people, right? But your phone, you want it to work with your voice, maybe the voice of you, and maybe the voice of your kid and your wife, right? So how can you make this transition from a general algorithm that is basically pretty good for everyone to an algorithm that is optimally good for you and only you? This is also, of course, related to this problem, right? You want to adapt, you want to have user adaptive systems, and this is something that is very related to the active learning problem. Okay, another direction that I think is very exciting, and it's also something that is going to open up a lot of directions, is what I call the dynamic learning. Okay, so typically when you think about a machine learning system, you think it as a sort of as a black box that has been only fed with a bunch of parameters that you have optimized using this optimization algorithm. But once it's trained, it runs, and it runs in a kind of predictable way, right? It uses a certain amount of computation. So some of the, one interesting question is if you could think about the learning task, not just as trying to make things as accurate as possible by choosing an architecture, by trying to make the best trade-off between accuracy and complexity, right? You wanna be able, so you can think that, every time I use a neuron, I pay a price, right? And actually, this price can be paid can be measured in the amount of sugar that you use in your brain to activate the neuron, or it can be measured in terms of, how many hardware resources is this machine using. Okay, so it makes economical sense to optimize a trade-off, right? To be able to look for good trade-offs between the two quantities. And this is interesting because now we are starting to understand how to design systems that are dynamic, right? Where the number of operations that they do is itself something that we can optimize, that we can adapt. And so this is actually a lot of applications. You can, of course, learn how to train things faster. So then you can parallelize you can make parallelization even more effective. You can learn how to you can learn in small systems, like for example in a small network, and then your model can learn how to generalize well on larger networks. Okay, so this is something that is very important if you are working on social networks. And then the other thing that I'm particularly very interested, as I said, is how this topic can change or can contribute to the complexity theory, right? Currently in science, there are many problems where the limiting factor right now is computation. Okay, so for example, simulating a molecule, as I said before, we don't know how to do it because we know how to do it, but it's just that the way we know how to do it is too expensive. So we need to learn how to do these things fast. And so, this is it's an area that I think it's pretty exciting. And then the last example, the last thing I wanted to point out here, that is also a very interesting topic, is what's called the learning with a knowledge base. Okay, so knowledge base is basically you could imagine as the sort of the safe box where you store everything you know. Okay, so you have concepts, maybe you know countries, you know cities, and you know that there's relationships, right? There's a city that is capital from a country, there are cities that are not capital from a country, and so you can imagine that everything you know is stored in a sort of a structure, okay, that is called a knowledge base, okay? And so right now, in many machine learning systems, they kind of operate completely unaware of that thing, okay? So for example, when you learn how to solve object recognition, you don't have any access to knowledge base, okay? And so, and in a sense, this reflects two different approaches to AI that historically has been very hard to combine. Okay, so some of the old AI research was interested in basically learning or developing AI that were manipulating symbolic objects, right? And manipulating symbolic things corresponds to a mathematical framework that has nothing to do with basically the geometry and linear algebra where the deep learning is currently using. And so an example is, for example, learning how to Google. Okay, so let's say, we all learn in 10 years or 15 years, we have all become experts at how to query Google, right? I mean, you know how to use it, but in a sense, a machine does not necessarily learn how to do it, right? I mean, if I say, okay, what is the best tapas restaurant closest to the university, right? If I type this to Google, it's not going to be a satisfying answer, right? I need to understand that Google might require a certain amount of, like messaging and expertise before I can get the right answer. So I have some colleagues at NYU who are starting to work in that direction, right? Basically, you ask a question, right, here, and you know that if you put this question into Google directly, you might not have the right answer. So you might want to reformulate the query. Okay, so learning how to reformulate things correctly so that the search engine can give you the good answer, this is potentially a game changer, right? It can have huge impact in the field. And I think that this is the last slide, and so this is again something that is particularly interesting to me as a mathematician. That in a sense, if this deep learning is most of the time, let's say, it's most of the time praised because it has a huge application interest, right? It can be useful in many companies, but it's also actually a very interesting and actually kind of a super exciting area if you want to work on hard problems, if you want to basically understand things that are currently not out of the scope of traditional mathematical areas. And so this is one of the basically the main focus that I mean, this is what I'm spending my days most, trying to think about these problems and how can we basically develop new mathematical tools to understand not just how to make these things better, but also to understand why they work so well. And so with that, I think this is my last slide. And so now I think I'm open for questions.
Hola, 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 hola. Well, first of all, thank you very much, Joan, for the presentation. Now we will make some questions from the panel. Well, for me, just 2 or 3. And then it will be an open mic for every one of you who want to participate, OK? I will keep it short. Well, the first question, actually, almost all the questions, you have answered them, so thank you for them. But I wanted a little bit more of detail on some of them. They are kind of basic and coming from more the industry than the research part. But the first one is related to what you have been telling about the differences of how research is somehow paid in US, where companies are highly involved in research, while here seems to be not so involved. And the question is, what can be done? Of course, if we had Google here, it would be much more easier. If we had companies that size, it would be much more easier. But are there other things at maybe a little bit more of a more little scale that can be done and can be applied right now?
Yes, I think that there's certainly room for more dialogue between the industry and academia. And I mean, to be honest, I'm not up to date what are the current activities here. So maybe what I'm going to say now, someone will tell me, yeah, we are already doing it. But just on the top of my head, one of the easily actionable things to do is if you have at universities here, like UPC, UB, or UAB, if you have let's say classes that teach machine learning or even like deep learning, have let's say final projects where it's actually mentors from industry that come and present, okay, here's my problem, here's my data, and here's what I tried, and can you do better? And so this is something that I think it really works both ways, right? Because sometimes we have the impression that when we think about academia and industry, that basically the professor is bringing, is giving knowledge to the industry, and then the practitioner is just say, okay, thank you very much, maybe here's a check. But actually, I think it goes really both ways, right? I mean, the goal of as a company, you might be a small company, you might be a bit put off by having to let an employee spend some extra time doing this, but actually I think it's very useful to the company, to the bottom line, right? Because what you learn interacting with students and maybe with the professor and the other projects is something that definitely you can bring to the company. So, and then of course, I mean, sending the students to do internships, that's something that is really present in the US. I don't know to what extent we could have models where you can help basically, I don't know, you can make it easier for students to spend time in companies, even if it's not in Barcelona, even if they have to go abroad. That's another suggestion. And then I guess that you are already, I don't know, you maybe organizing summer schools. That's another thing that can be potentially interesting. Barcelona, I mean, we were just having this conference here of Applied Math. And everyone is so happy to be in Barcelona, right? I mean, you really have a nice city here. So it should not be it should not be very hard to actually, help organizing more machine learning conferences. Maybe, inviting a bunch of people just before the conference so they can, basically interact a bit more and establish a networking relationship.
Okay, thank you very much. Another question is more related about deep learning applications. You have told about deep learning applications more into the research field. It was very cool, the thing that you showed us about how to apply it to physics and particle theory. So my questions were more related to business applications. So what kind of cool or interesting business idea, startup idea have you heard recently that involve deep learning or machine learning in general, but if it could be deep learning in particular, it could be nice.
Okay. Well, there's one. So I don't know to what extent they use a lot of machine learning, but certainly they use some. Is this a little device that you put on front of your car on the dashboard that creates like a virtual screen? So basically, the mission is to help people. I mean, you basically give up on the idea that people are not going to be using the cell phones while they are driving, right? I mean, it's too strong to give up. So what you do is that you make it safer, right? So basically, you have a system where you can overlay information in front of the dashboard, and this requires a little bit of machine learning, right? Because you have to basically, detect where the person is looking. You need to make sure that you have to interlate way. You have to be, you have to be sort of in between the driver and the road, right? And so this, of course, is a complicated thing that you can only model with data-driven. I don't know what else.
It's okay, yeah, sorry.
Okay,
because,
yeah, sorry about that, yeah.
No problem, no problem. And finally, the last question from my part, it's related with how to learn deep learning practically. So many people here have experience in data science, in more classical machine learning, and some of them are doing courses or learning stuff by themselves about deep learning. What would be your advices in terms of increasing the knowledge for those people that already have the background in machine learning to go deeper into training with deep learning?
Okay, so maybe what I would suggest is maybe rather than spending all their time, because probably time is the limiting resource for these people. So rather than spending all their time, coding and doing tutorials on, let's say, PyTorch, TensorFlow, try to keep some time also to read. There's a growing literature on basically fundamentals of deep learning. So maybe, this idea that if you want to learn deep learning, why do you want to learn it for? Maybe you want to just, learn the minimum amount of thing to just use as a baseline, basically to be able to run the model and to, just press a number and get the result out. But if you really want to make it really useful, this might not be sufficient, right? And you might need to have some guide. You need to be able to make changes to the architecture that are informed. And this is typically something that you cannot acquire in 2 days, right? I mean, I saw that there was this nice deep learning class by UPC. I think that it's an initiative that has been, I think, going for 2 years. And so this is something that, is really an important first step, right? Because this is it's very hard to magically acquire. It's not a magic tool, right? That just learning 2 TensorFlow tutorials is going to give you. I mean, there's people who have been working on this area for a while, and we try our best to communicate what we learn in the form of papers, in the form of classes, courses. So I would really tell them not to underestimate how important it is to actually go for the fundamentals.
Okay, and that's all from my part. So if there's anybody in the public that wants to ask any questions, if you know, I have more questions, so.
Hi, I'm Davide, and I have 2 questions. One might seem trivial to you, but I'm just curious. And what's the difference between the symbolic space that you have described and any other Hilbert space?
Sorry, I didn't understand.
So what's the difference? What's the difference between the symbolic space that you have described for the word embedding, for this new kind of word embedding, and any other Hilbert space that you can describe with the
yeah, in the symbolic space, you have basically discrete objects and discrete rules, right? So basically, you have a list of countries, and there's only 500 countries or whatever, and there's a number of relationships that are 1 over a discrete family. So this is what I refer by symbolic, right? And so the big problem is that if you want to learn in that space, you cannot use the basically the gradient-based learning, right? You cannot look at the current model and say, well, how can I do a small change in my model so that it will behave a little bit better in my loss, right? Here, the notion of taking a small step doesn't exist. Like mathematically, it's not defined if you have a discrete space. And this is something that historically has been a big difference between basically the AI community is basically separated in two, right? The people who were more developing symbolic logic and basically AI that were operating in that world, and then more traditional machine learning that is always cast and is always presented as basically learning over a Hilbert space or a Euclidean space.
And the second question, it's usually when you go in front of social scientists, especially economists, and you present deep learning as a tool, they usually say they like it, but they don't use it most of the times because they are more concerned about causation. And they criticize that it's just on prediction, deep learning in general. Do you think that this is true, or do you think that there's room also for causal inference through deep learning?
Yeah, so this is a good point, and it's really something that certainly we are aware, right? That if you use it for prediction, it's not going to be enough, right? There's a lot of, basically the scientific method is not about just doing prediction, right? You emit an hypothesis, and then you try to invalidate the hypothesis, right? So right now, if you just have a sort of a deep learning model that just has been trained to be good at classification, it's not something that can be used in this statistical setup. So as I said, there's hope, right? There's actually people who are starting to use basically probabilistic graphical models to do causal inference. Of course, there's people who have been working a lot for many long time in basically graphical models that that have the ability not only to do predictions but also to do more complicated inference. And also related to what I said, in some domains, like if you make it very specific to a domain, like you were talking about economics, for example, in physics, I have the same problem, right? In physics, one of the things that is interesting with these models that I described based on graphs is that you can take their physical model, for example, something that is called a QCD kernel aware. So basically, they have an idea, a preconceived idea on how you should be comparing particles, but there are some parameters in this model that they don't know. So if your model is really expressed in these parameters and you train them, then you can really interpret these parameters, right? Because they have a physical meaning. And so there's, in a sense, the setup here is sufficiently flexible and general that you can accommodate. But what is clear is that if you take an off-the-shelf model that was designed to do classification, you shouldn't be asking it to do causal inference, right? Because it was not designed to do that. So if you want it to do that, you have to change it. You have to do some part of the work.
More questions?
Well, then I have a little bit more questions here. Also from the practical point of view, we have seen a lot of advances. Well, deep learning has been used a lot in text, images, videos, sound. You have showed us also more applications. But do you think deep learning will or is going to be used in more typical machine learning problems where the dimensionality is lower and maybe you have also less data?
Yeah, I mean, this question in a sense depends on what is your definition of deep learning, right? And people don't really agree. I mean, if it's really this, if it contains all the models that can be trained end to end, right? Where just computing the chain rule, then the answer is yes, right? Because there's as I try to describe, there are a number of there are multiple ways where you can enhance or update sort of these neural networks to accommodate different constraints, right? If your constraint is that you want the model to be more interpretable, well, maybe there's ways where you can, as I described, to make it a bit more explicit. But of course, there are limits. I mean, it's also important to understand which are the problems for which these models are not working, right? They are not effective. And for example, there's a very notorious example from, let's say, online click advertisement, right? Like Criteo or like these companies who do ad placement, they need to make decisions in, I don't know, like milliseconds, right? Like tens of milliseconds. And they need to leverage huge quantities of data. So there's physically not enough time to run a deep model, right? You are really constrained by the physics, by the hardware, to make a very fast decision. So this is really putting a constraint on the architecture, and so then you can call it, logistic regression. So it's not a deep learning per se. But this then becomes, the distinction becomes really how many layers your model has, right? I mean, if it has one layer, then it's, well, maybe then it becomes to a classical machine learning problem. Then there are, I mean, of course, other domains where, I don't know, for example, like, for example, speech processing, right? So right now, before, historically, you had, the pipeline was very, very complicated, right? You had the first step that was using these sort of hand-engineered features. Then you had maybe a step of deep learning, and then you had the last step of like HMM, right? Which is a sort of a inference on a graphical model. And the trend that we see in these problems is that the more you realize that you have to train these things end-to-end, by basically seeing everything as a different neural network, typically, well, I mean, actually most of the time has resulted in gains, right, in something that is more efficient. So I really believe that this philosophy of training things end-to-end is actually, a powerful one. I mean, that said, it's not, you can also argue that, and in a sense this is related to another of the current trends in machine learning, in deep learning, is that the different tasks, right, might have something in common, right? I mean, you might be using like a data set to train a model how to walk, maybe an agent how to walk, and another problem might be, okay, I want to learn how to, maybe how to lift an object. So maybe these two tasks have something in common, right? There's some knowledge about how to operate the muscles that is shared between the two. So again, this is something that you would lose if you just do end-to-end learning for task 1 and end-to-end learning for task 2, right? Because then the two models, they don't talk to each other. So as I said, so this is another trend, that if you believe that that you have two tasks that have some knowledge that they share, you have to figure out a way to train them together. And this involves sometimes maybe breaking the task in several.
Okay, do we have a microphone? Sure. Here. Here.
Hi. Thank you for the presentation. It was really interesting. One of the things that you were talking about was the project that you have with SAP, right? I was just thinking, guys like Steve Jobs, who was an underachiever, or Bernie Madoff, which ends up, stealing from so much money from so many people. What would be taking us in a career path, for instance, like if you are evaluating, analyzing thousands or hundreds of employees or potential guys that you want to work with, what would be taking as a leader, let's say, or as what would be the goal for SAP to consider? Who would be considered, let's say, a successful person as
Yeah, I mean that's a good question. I mean, in the context of SAP, perhaps they are not looking at this useful. I mean, they are more interested in the bulk. Maybe so they have this notion of knowledge worker, which corresponds like the employees who have like a like significant added value to the company, to the bottom line. But it's true that in all these problems you always have outliers, right? People who are really not described by the bulk. So I don't know then in that case if there would be like a like a business case where why would you want to learn a system that also encourages or that includes that sort of profile. I would be personally interested, right? I mean, if you were like starting your undergrad and you would say, okay, just to have an idea of what did people that I reflect myself on, what do they do if they were in my position? So this is something that we could now conceive to learn and to train on.
There's so many human factors that say that
yes.
It would be so difficult to predict where are you going to be in 20 years from now?
Exactly. No, but I mean, I completely agree that here we are trying to, quantify something that is very, let's say, every human and every person is unique, right? But the question is, well, maybe the one choice is to declare that there's nothing to be learned, and you just declare that everyone is basically related to what I said, right? Do you have anything to learn from the bulk of people who have something in common with you, knowing that there will not be an exact prediction, but there will be maybe something in common. And the question is, does it have like a value to the company or to the employees? And so in a sense, that's the goal of the project, to figure out precisely if this is something useful or not. And so I'm assuming that this is not a new question, right? Many people who have access to large databases of people and employees are already starting to think in these terms, right? I don't know.
Thank you.
Okay, so that was all. Do you have? Yeah, there's a last question here.
You gave some examples about the graph neural nets. I'm not too familiar, or not really familiar with them at all. I was wondering, one, can you explain a little bit about the architecture? So like the inputs, is it just that you pass the edges or something, or is it like really some specific algorithms, learning algorithms for graphs specifically?
No, so yes, so this is actually an architecture that is pretty flexible. So there's one first setup where, yeah, you might, your input data is relational data, right? Let's say that we take the example of a social network, right? The only thing that you measure is who is friend of who. And you want to derive, maybe you want to take this as an input, so you can imagine that your input is the whole graph. Basically, you can encode it with, the adjacency matrix. And then at the output, you might be interested in maybe, I don't know, maybe you want to detect whether this community is of, maybe has, basically if this graph represents, let's say, 2 communities or 3 communities. You could think this as a classification problem. Or you might be interested in basically estimating a label for every person in the graph. So in that architecture, the input is the graph itself, and the parameters that we learn, you can think them as like linear combinations of operators on the graph. Okay, so I'm assuming that you are a bit familiar with this. So basically, you can define for every graph, you can always associate operators that are sort of called diffusion, right? You can basically, take a signal and blur it. So you can define a family of these operators, and then you can learn how to combine these operators with these nonlinearities to predict the best possible thing at the output. And so if you are interested, I can point you to some of the references, but it has a lot of similarities with a standard like graph processing algorithm, for example, spectral clustering or message passing algorithms. So if you are familiar with those, this is a kind of a neural network version of these algorithms.
What are those typical unsupervised learning problems?
Both. We do mostly supervised. With supervised, you can already apply them to a lot of problems, but you can also use them to do like a generative model. So we have some recent work where we use these things to model surfaces, to generate surfaces. For example, you can, and this is something that of course can be useful in practice, right? If you can, learn how to represent like an object and be able to manipulate it, right? To generate new objects that have like the properties that you care about.
Thanks.
Okay, I think that's all. So thank you very much, Joan, and thank you very much, the audience. Today we don't have beers. Usually we have beers at the end, but we hope to see you in the next event. Okay, so thank you very much.